Hey kids, welcome to chapter 5. And unlike most of my videos, I don't do the warm-up in the video, but these two problems, I really need to make sure you have these skills going forward because we're really going to be doing something completely different than, we're going to be solving differential equations, but with a completely different mathematical process. And hopefully you see a hint by recognizing that I'm going to assign or define Y to be an infinite power series, where each term of x, right, x to the 0, 1, 2, 3, and 4, has an arbitrary, has a sub n, has a constant in front of it. If you can find y prime and y double prime in the same format, y prime, right, the derivative of a constant is 0, so on and so forth. So hopefully you can see, that in my summation notation, I would have n times a to the n, x to the what? N minus 1. But your index wouldn't start at 0, would it? Where would it start? Right, it would start at 1, right? Because my first term is actually 0, but I want the first term I see to be a sub 1. So the same thing is going to happen with the second derivative, right? Certainly I'm going to, and of course I don't need to write that, but I'm going to have 2 zeros and then a constant, yada, yada, yada. So this summation notation would be n minus 1 times n, a to the n, x to the n, what? Minus 2, and your index would start at 2, right? Because this is my first term. So we are going to be dealing with a sub 0 and a sub 1, as long as you're going to the second derivative, as being arbitrary constant. Kind of think of those as our c sub 1 and our c sub 2 previously. So that's one skill. The second skill, I don't expect that to be too hard, but the second skill, we didn't do this in calculus, and I don't remember in the pre-cal series unit if we do any of this manipulation of sigma notations. But for differential equations, you may be wanting to add, right, derivatives together. But notice that in my second and first derivative, I don't have x to the n like I do in y, my solution. So can you manipulate y double prime to be an x to the n? Well, again, I don't remember if you did this in pre-cal, but if not, I'm going to tell you how. Inside the summation, I can add 2 to every n, as long as I balance that out with subtracting 2 on the outside of the summation. So I end up with n is equal to 0, infinity minus 2 is still infinity, n plus 2 minus 1 is n plus 1, n plus 2, a to the n plus 2, and x to the n. Can you do the same thing with y prime? This time you don't have to add 2. What do you have to add? Right. Add 1 to all the n's on the inside, subtract 1 on the outside. So that ends up being infinity minus 1 and still infinity. Right, and then if I wanted to add y, one of the properties of summations is as long as you have the same power on n, I can factor that out front. And if I have the same index here, I can use one summation. and put everybody inside, right? That we're also going to need to use in this section. So we're going to go back. Chapter 4 was higher order, right? We're going to go back to second order, and we're going to go back to second order homogeneous, right? Which means you're equal to 0. So you've seen this before. It's just that we had P, Q, and R as constants, right? Where we use the method of undetermined coefficients and method of variation of parameters. P, Q, and R were constants. So what do we do when they're not constants? They're functions in terms of x. Oh my gosh, don't know what to do. Well, one of the things we're going to do is make some rules. And in order to make our life easier, we are going to assume that PQ, of all the functions in all the world, we're going to assume that they are polynomials, right? And as long as they, right, and this process would work even if they're not polynomials, as long as they're analytical, which means you can write them in terms of, right, a function in terms of x. But the polynomials are easier to deal with. I heart polynomials. We're also not going to have repeated factors. That just makes our math uglier. If you take a center of a power series expansion, plug it into the function in front of y double prime here, and as long as you plug that number in and you don't get 0, then that point, that center, x of 0, comma, not 0, is called an ordinary point. And the solution to the differential equation behaves similarly to this function in some interval, you should write with power series, radius of convergence, around the center. If that's not so, if that is so, then we are going to make a power series solution. If that is not so, we have to use another method, which is later in this chapter. When you plug in the center and you do get 0, you want to have a way to investigate the behavior around that singular point as opposed to the ordinary point. That would not work for what we're going to do in this section. All right, so I'm going to give you a list of directions that may or may not make sense to you until we're doing them. Hopefully after we do a couple, it makes sense. So we're going to assume the solution, y, can be written as a power series expansion. And then we're going to look at our differential equation and see which derivatives we need to find, right? Now, we're going to be dealing with second order, so that you're going to need to find y double prime and y prime. Although my first example is just going to be a first order, again, just try to oversimplify the problem as I'm showing you this technique. Then you're going to substitute into the differential equations. Sometimes you're going to have, right, functions in front of your summations, right? Not for our first examples. I will show you that in example 3. But if you do have a function in front of a summation, you need to get it inside. You need to distribute it inside. We will do that in an example 3. You need to manipulate all the summations so they all have an x to the 1. That's why that number 1 of the warm-up was there. Then number 2 of the warm-up, manipulate the summation so they all, I guess that was number 1. I'm sorry, this was number 2 of the warm-up. Manipulate the summation so they all have x to the same power. And then as a result, in our warm-up of manipulating x to the n, we got the same index. That isn't always necessarily going to happen. Hint, if you have to do step 2, this part. Then you're going to combine into one summation with the x to the n's factored out. And then you're going to kind of sort of do undetermined coefficients thinking. You're going to equate coefficients. For a power series, right, a sub 0 is the same as, right, the coefficient of the first term is the same as the function at the center. And the coefficient of the second term is the same as the first derivative at the center. We're going to call those our arbitrary constants. But to find the rest, right, this is a sub n when n is 0, and this is n plus 1. We're going to find a recursive rule for a to the n plus 2. How we're going to do that is making a table. And this is the part that probably won't make sense. You're going to have your n's here, your a to the n plus 2's here, and then you're going to have your rule here, and you're going to want to write all of these in terms of your arbitrary coefficients. Then you're going to look for a pattern, and you're going to be able to write a rule for the solution. All right, so let's do one. I want a power series solution, no shift on x, for the differential equation. So remember, step one is you're going to assume the solution is in this form. I'm going to get my power cord here. And as I told you, the first example is just a first order. So all I need is the first derivative minus the original, y. But I need to manipulate so that I have both of these have an x to the n. Add 1, add 1, add 1, outside subtract 1. When I did that, not only did I get both of them with an x to the n, the indexes do match, so I can write 1 sigma and then equate coefficients, where I was equal to 0 is my constant, but I don't have any constants. I just have coefficients of x to the n, so it must be a 0. So take that part out, look for your highest index. On A. So a sub n plus 1, that's higher than a sub n, so get a sub n plus 1 by itself. Bam. Now remember, in the list I gave you, I said get a, right? You're going to be dealing with a sub n plus 2, write a recursive rule for that, but that's a second order. This is a first order, so I just need a sub n plus 1. So now I'm going to make my table. I'm going to use as many rows as I need until I see a pattern. So when n is equal to 0, a to the n plus 1 is equal to this. A sub 2 is equal to Now, what I want is to get all of these in terms of a sub 0. If it was second order, I'd want to get them all in terms of a sub 0 and a sub 1. Here's what I mean by that. A sub 1 is a sub 0 over 1. Whoops. 1 plus 1, silly. So this is 1/2 times a sub 1, but look what a sub 1 is. This is 1/3 times a sub 2, but look what a sub 2 is. Can you see the pattern? Oh, hey, a sub n is equal to a sub 0 over what? N factorial. Right? So a sub 0 is equal to a sub 0 over 0 factorial, which is just 1. A sub 1 right, is equal to a sub 0 over 1 factorial. Same thing. A sub 2, right? A sub 0 over 2 factorial. A sub 3, right? Crazy, crazy. So remember what we said our solution was. We were assuming our solution was you just found a sub n. Oh, snap. So here's my y is equal to a sub n. I put in a sub 0 over n factorial. Whoa, 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 whoa. Look at the little magic I did with multiplication. Hey, what is the summation of n equals 0 of x to the n over n factorial? What is that? Are you telling me that y is equal to a sub 0 times, what is this? What is this? I'm not worthy. Oh my goodness, that's e to the x. Hold the phone. An arbitrary constant times e to the x is the solution to this differential equation? I think so. What if I had not said I wanted a power series? You would have done, well, that's r minus 1 is equal to 0. R is equal to 1. Therefore, y would be equal to an arbitrary constant, e to the 1 times x. Oh, math is cool. Math is cool. Right? Crazy. Let's do another one. All right, I want you to find a power series solution. No shift on x. This time I want the second derivative plus y is equal to 0. Do the same shift. Put it into 1. Equate the coefficients. Look for your highest index, get it by itself. Make a table. So this time, fill it in all the way down. And again, if I need more rows, I'll make them to see my pattern. So this time it's a second order, so I want to try to get everybody in terms of a sub 0 and a sub 1. So this is 1 over 4 times 3 times a sub 2. Right? Isn't this 2 factorial, and this is 3 factorial, and this is 4 factorial? Can you see what's going to happen? Whoops, I'm sorry, I lost the negative here. This was negative, so this one was positive. So this is negative 1 over 5 times 4 times a sub 3, which is negative a sub 1 over 3 times 2, which is positive a sub 4, which is positive a sub 0 over 4 factorial. So this is negative a sub 0 over 6 factorial. All right, let's see if I have enough here to build a pattern. All right. I don't have a clear-cut pattern for all of them like I did with the first, but I definitely see, can you see everybody that's got an a sub 0 in it? Everybody that has an a sub 0 has what kind of factorial? Even, right? So now this is going to get a little, this might make you feel a little uncomfortable, but let me do this. Let me say that when n, let's let n equal 2k. When n is even, and I'm going to start with k equals 1. When n is even, the signs alternate, don't they? Right? Do you see I have negative, positive, negative, positive, right? The signs alternate, and then all of them have a sub 0 in the numerator over what? 2k factorial. Truth? Right? So that's all when n is equal to 2k. So I have that scenario. But then I also have this scenario. All my a sub 1s have what kind of factorial? Yeah, odd, right? So I'm also going to let n equal 2k plus 1 when k starts with 1. So I still have my sign alternator. These ones all have a sub 1s, but the factorial is odd, starting with 3, right? Factorial. So how do I write my solution? My solution then is going to be a linear combo of my even pattern and my odd pattern. So y is going to equal a summation plus a summation. What's my first one going to be? What am I missing? Remember what we assume our solution to be? You found a to the n, right? You just found two different a to the n's. You found this one when n was 2k and one was 2k plus 1. So actually, I guess I should write k here, shouldn't I? Oh, kind of gave something away. Gosh darn it. X to the n is equal to what? 2k, right? plus also negative 1 to the k, a sub 1 over x to the right? That's my solution. That's my power series solution. Now remember, a sub 0 and a sub 1 are arbitrary coefficients. So I can osmosis them out to the outside. You see what's happening? Do you see it yet? Oh my Lanta. Have you seen a power series that looks like this? Now, again, I know the switch from n to k is a little bit weird, but I just didn't want to use n again because n, they weren't the same as over here. But nevertheless, do you recognize those? Right? Isn't this is just even powers over even factorials, signs alternate. Odd powers over odd factorials, signs alternate. Oh my gosh, who is that? Sine and cosine with arbitrary constants in front. What is happening? What is happening? Remember, we started out trying to solve y double prime plus y is equal to 0. What if I didn't want a power series? Wouldn't you say that is r squared plus 1 is equal to 0? So r is equal to plus or minus I. So you would have, right, e to the 0 in front of this, e to the 0, which is just 1, c1 cosine of x plus c2 sine of x. Oh my gosh, that's what we have. We had y is equal to a sub 0. Okay, that's my c sub 1. Cosine, so what was that? That was, oh yeah, that was the evens, right? Plus, I mean, life is, it just can't get any better than this. What is happening? They're the same thing, right? Now you're used to thinking of cosine and sine, right, being built from the unit circle and triangles over there, but I can also get it from the solution to a differential equation. What? So good, so good. All right, let's do one more example. There's a lot of things in these next coming sections and chapters where they'll refer to these famous equations. They're famous equations in physics and astronomy and all this, right, kind of stuff, right? You don't you don't have, it's not like Pythagoras or anything like this. So this is called Aries equation. I don't really know why. I can't remember, but I think he's astronomy, but I don't take my word for it. But anyway, no one is going to care if you recognize that y double prime xy is equal to 0 is Aries equation. All right, so what do we have to do with this? So start out with your second derivative, right? I need y double prime. Now, can we skip right to this scenario? Right, where I already shift the index? Right, is that okay? Minus, remember I told you what was going to happen? In example 3, right? You have a function in front. So Whoops. Oh no, I already shifted it. Silly. I was thinking I wouldn't. All right, so I've got x to the n's. I've got the same index. The issue here, though, is that I've got that x in front. I can't deal with that. I have to move that inside and combine it with this x. So when I do that, darn it, what do I get? I move that in here, it's times x, which means I really have x to the n plus 1. Dagger. What do I have to do now? I have to get that to x, so I have to get this to x to the n. To get it to x to the n, I need to subtract 1. And if you subtracted 1 on the inside, what do you have to do to the outside? That's right, add 1. So things are getting worse and worse. I fix one thing and I create another problem, because now what's true? Right? Now what do I have to do? Well, crap. I've got an index here. If I go try to fix this index, I'm going to, right? What do I do? So remember, we haven't had to deal with this before, because every time we've fixed an x to the n, we fixed the index just automatically got fixed with it. So this is a new situation. Not only did I have to deal with that x in front, but now I also have to deal with the fact that my index isn't the same, and I don't want to mess with shifting this index back down, because that's going to mess with the x's. So in order to deal with an index change where you don't want to affect the powers on x, is you can't, instead of bringing this down to 0, you're going to move up. Move low index up. How I'm going to move low index up is I'm actually going, like when you think about way up here, okay, so if I have y is equal to x is equal to 0, let me just put a to the 0 plus x, a1, x to the 1 plus a2, x to the 2, blah, 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 blah. I could just say, hey, I could start this at x to the 1. Instead of starting at x to the 0, I could say y is equal to a to the 0 plus, why do I write n? I mean x over there. N is equal to 1 to infinity, right? A to the n, x to the n, right? So that's what I'm going to do here. I'm going to use, I want to get up to n to the 1. So I'm kind of going to suck out my plug in n is equal to 1. When n is equal to 1, what do I have here? I'm sorry, when n is equal to 0. When n is equal to 0, I have 2 times 1, a to the n, x to the 0. Truth? Isn't that just 2a to the n? You sucked out that first term when n was equal to 0, which lets you now add when n is equal to 1 and not change. See what I did there? And now I have matching indexes and matching powers on x. And now I can go about my business, just not forgetting that you have this extra term out here, 2 to the a sub 1 plus 1 summation with an x to the n equal to 0. I kind of dropped my equal to 0 going along. And what's in here? Minus is equal to 0 plus 0x to the n. But you're going to need this 0 this time. Do you see that? There's equating one coefficient. There's equating your constants. So I'm going to go up here. And I'm going to say 2a to the n is equal to 0. Therefore, a to the n is equal to 0. Whoops, that's not a to the n, silly. That's a to the 2. I was like, wait, I can't have my a to the n be. Then I also have is equal to 0. Take your highest index. Who's your highest index? Right? So this is my recursive rule. Yes, I am dealing with the fact that it's a sub n minus 1 this time. Oh well. And I'm going to make myself a table. N, a sub n plus 2, which is equal to a sub n minus 1. Then I'm going to go down, I don't know, maybe to 5. So when n is equal to 0, that's you get a to the 2, but we already know that's 0, right? Remember that? That was our constant. So how about a sub 3? A sub 3 is going to be a sub 2 over 3 times 2. Whoops, I'm sorry, a sub 0, right? Because n is equal to 1. So let's just, we kind of starting to see maybe we have a factorial situation. So a sub 4 is going to be a sub 1 when n is equal to 3. Oh man, I am not doing my table very neatly, am I? Should have just printed it, shouldn't I have? A sub 5 is going to be a sub 2 over 5 times 4. And lastly, now let's go. Remember I said what you want is you want to get all of these in terms of a sub zeros and a sub 1s. So done. What can I do over here? This is 1 over 5 times 4 times a sub 2. But a sub 2 is 0. Oh, snap. This is 1 over 6 times 5 times a sub 3. I don't think my factorial, right? I was thinking, oh, this is going to go the factorial route, isn't it? No, it's not. I'm missing a 4 there because this term went to 0. Rats, I love my factorials. What is this one? All right, so let's see. Can I write a pattern? So far, what do I have? I can see that my, what do you have? Look at what I have for all my a sub zeros. What do I have? For my a sub zeros, I've got, right, 1/6. Now don't forget a sub 0 we have from the beginning. I should put a 1 here, right? Because remember, we have a sub 0 and a sub 1 are arbitrary constants, and we're assuming that y can be written as a to the n, x to the n. So there's a to the 0 plus a to the 0, 1/6 x to the what? Right, because this is x to the 0, right? So then where do I go? So I've taken care of that. Do I have another a sub 0? Oh, yep, down here. What is that? 30 times 6. 180. X to the what? What term would this be? Dot, dot, dot. And how about my a sub 1s? Again, you're going to get what's a sub 1 in front of in your power series. A sub 1 is in front of the x to the first term. And then what do I have? 1/12 x to the 4th. So I don't need this one. Got that a to the 1. Here's another a to the 1. 1 over, what is that? 12 times 42. Geez, 12 times 42. 504. Check with my calculator here. Yep, all right. X to the 7th. There's no real pattern to write there. So this time I just wrote, right, there's my a sub n, but my a sub n's I had to write in kind of two separate patterns because they involve, the a sub n either involves a sub 0 or a sub 1's. So my power series solution is just a big old y equals, right, the sum of those. So I have a, right, a 0 power, a first to power. Remember, the second one is a 0. The coefficient was 0. And there's the third and the fourth. And then I have a coefficient of 0 and then a 6 to the 7th, right? That's as much as I need you to do. All right. Well, this was just, more fun than a box of chocolates. It was more fun when we got the e to the x and the sine and cosine x. But honestly, if we're going to get those, then we don't really need to write a power series. So for this Aries one that apparently is pretty famous, it didn't work out to be a nice pattern. But we still wrote a power series solution that all in terms of, right, powers of x, all with the arbitrary constants C1 and C2, like we did in the chapter 3, right? We always had a C1 and C2 unless I had an initial value problem. I just call them a sub 0 and a sub 1 here. All right. So we'll just have so much fun with more of these problems. And we'll do an initial value problem also in our live session. And I will see you then.